Hello students, so in this lecture we will be talking about optical properties, mainly at interfaces, that is at thin films. So if we have a beam of light incident at an angle theta 1, at an interface separating two mediums. One is having refractive index at n1, another one is having refractive index no, and this beam line gets refracted uh, by an angle phi o in the second medium. Then the ratios of the reflected and incident, transmitted and incident amplitudes are given by the following. So we have amplitudes R, which is the reflection amplitudes. We call it as reflection amplitude. We will have T as the transmission amplitude. So that's first at the relationship. So there is one relation called R1P. It is basically equal to NO cos phi 1 minus N1 cos phi 0 divided by N0 cos phi 1 plus N1 cos phi 0. Now this R1P is actually called the Fresnel's reflection coefficient. And it is basically the ratios of reflected versus incident amplitudes. So call it ratio of reflected by incident amplitudes of waves coming. Now the suffix p, it indicates that the vector lies parallel to the plane of incidence. So there are basically two components. One is R1P and another one is your R1S. Now R1S is for the vector lying perpendicular to the plane of incidence. So there are two components, one parallel to the plane of incidence and one perpendicular to the plane of incidence, and the value of R1S is n1 cos phi 1 minus n0 cos phi 0 divided by n1 cos phi 1 plus n0 cos phi 0. Similarly to R1, which stands for the reflection coefficient, we will have T1 transmission coefficient. So again we have two components of T1. One will be T1P vector parallel to the plane of incidence. So that will be equal to 2n1 cos phi 1 divided by n0 cos phi 1 plus n1 cos phi 0, and then again T1s perpendicular component will be 2n1 cos phi 1 divided by n1 cos phi 1 plus n0 cos phi 0. Apart from that, we have the usual Snell's law, which says that n0 sin phi 0 is equal to n1 sin phi 1. Now for normal incidence, these equations are simplified, and the difference between this plane of polarization, whether it is perpendicular to the plane or parallel to the plane, this is no longer existing. Now next term that we are concerned one is called the reflectivity or reflectance. It is also called reflectance. R, and it is the ratio of the reflected energy to the incident energy. Since the reflected and the incident energy are the same direction, so let us put it as ratio of reflected to incident energy. Again, since it is a matter of energy, so whether it is parallel to the plane or perpendicular to the plane will not matter. So if we have Rp is equal to basically your Rs, and it is actually equal to R, either you can put it as R1P whole square, or it is also equal to R1S whole square. Right. Similarly, like reflectivity, we have transmittivity. T and T is, so we have TP is equal to, here the ratio of the refractive index will come into play, n0 by n1, T1V whole square, and we'll have Ts as n0 by n1 T1s whole square. However, in this case, Tp may not be equal to Ts because the transmitted and incident directions may not be the same. Now for normal incidence, this Rp will be equal to Rs, and it will be equal to n1 minus n0 divided by n1 plus n0 whole square, whereas in this case Tp will be equal to Ts only for the normal incidence, and it will be equal to 4 n0 n1 divided by n1 plus n0 whole square. Now there is a case if the substrate is an absorbing medium. Substrate is an absorbing medium. It has a tendency to absorb light. Then we have to replace n, write n as n0 minus ik0, where k0 is the absorption coefficient. So in this case Rp will be equal to Rs, so there might be a little change, that will be n1 minus n0 whole square plus k0 square divided by n1 plus n0 whole square plus k0 square. This is the expression. Now we would like to understand the variation of reflectance with normal incidence. Then if you plot the reflectance R, which is given as percentage with respect to optical thickness, or wavelength / wavelength, then we get actually for uncoated material we will get a plot like this. So this stands for uncoated material. So whereas for a coated material you get a plug like this. Okay, so this is your uncoated. And this is, for example, is glass having a refractive index of 1.5, and if we increase it, and now this so basically what we are talking here is we're talking here of a system that is an N1 refractive index system over an N0 refractive index system. So N1 here N0 is actually equal to 1.5. Now this value, when you increase in refractive index, the reflectance value will increase in the case of coated material. This is 1.75, whereas this one will remain the same, and 1 will be equal to 2.0. So what basically this distribution is the representation of the reflectance as we go from N1 to N0. So this one stands for this N1 value. Now this one stands for the N1 value, and this is actually the uncoated, I mean this part. Okay, so this is how the reflectance changes. Now there is one equation which is called Brevis Test Law, which is given as N0 is equal to N1 tan phi p. This phi p stands for the polarizing angle. Okay. Now what happens is a point of interest is that the P and the S components of reflected beam have different amplitudes for non-normal incidence, right? So as we have seen, the P for non-normal incidence the P parallel to the plane and perpendicular to the plane, these components have different amplitudes. Now for a reflection from a transparent material, the P component goes through a minimum of amplitude and a phase change of pi. So whenever you are doing a this P component, this will go to a minimum amplitude, and it will also go through a phase change by at an angle greater than a particular angle called polarization angle. So this angle is the limit which actually not allows this P component to change. So whenever there is a phase change occurring, that means that P is converting into an S, the angle has to cause this polarizing angle. So this is the angle that is given by Brevis Test Law, as I discussed in the previous case, as is related to the ratio of the refractive index of the two phases. So these refractive index values will determine at which angle the phase change may take place. Now for reflection and absorbing surface, both the amplitudes and the phases of S and P components are different. Thus, the resultant reflected light is electrically polarized. Now, whenever we are talking about an absorbing surface, in this case what happens, both the amplitudes and the phases, we have one amplitude as well as phases of both S and P are different. Therefore, it implies that the reflected light is elliptically polarized. Therefore, it can be also written in a special way for absorbing surface and for elliptical polarization. It is written like RP RP by RS is equal to e to the power I delta tan psi. Where delta is the relative phase difference. This is the relative phase difference and psi is called the azimuth. This is actually the ratio of the reflection amplitudes of P and S components. It is the ratio of reflection amplitudes of S and P components. Now, radiation and absorption occurs in majority of media, and the intensity of radiation is generally attenuated in an exponential form. So radiation and absorption, which is very common in majority media, and this radiation, it undergoes an attenuation. That it decays, and it decays in exponential form. It's called e to the power minus kt. K is absorption coefficient, and T is of course the thickness, and so absorption coefficient K, and it is equal to 4 pi small k by lambda. Now this absorption is of fundamental interest because of its relationship to the dynamics of electrons and ions in the medium, influencing the electromagnetic radiation. So absorption actually is an interesting phenomena, or it is actually searched for because it actually influences the electromagnetic wave by influencing the electrons and the ions in the medium. The absorption of electron and ions affects the electromagnetic radiation that is taking place from medium. Now, an absorbing medium is basically characterized, what is called an absorbing medium, is characterized by a dielectric constant. So this dielectric constant has got a real part, epsilon 1 minus I epsilon 2, and it is also equal to 1 plus 4 pi alpha, where alpha is the sum of the probabilities resulting from free carrier bound carrier interband. So the bottom line is that epsilon 1 is equal to n square minus k square, and epsilon 2 is equal to 2n small k which is equal to 4 pi sigma by omega, where omega is the conductivity and sigma is the conductivity and omega is the angular frequency of the so omega is the conductivity and omega is the angular frequency of the incident light. Now this absorption is mainly because of this conduction that is taking place of the free electrons, as in the case of metals. The conduction has a very strong role in the absorption of optical absorption. Now there are other relationships connecting the dielectric constants with optical constants. So for example, epsilon 1 is equal to n square minus k square, which is equal to 1 minus omega e square divided by omega square plus omega 0 square, and epsilon 2 is equal to 2n small k, which is again equal to omega square p divided by omega 0 divided by omega square plus omega 0 square. where omega p, the polarizing angular frequency, is 4 pi 4 pi Ne E square divided by m star to the power 1 by 2, and this is in free space. And omega 0 is equal to, sorry, this is actually the plasma frequency, not the polarizing frequency, and omega 0 is equal to 1 by tau 0, and it is equal to Ne E square divided by m star sigma. Now, this omega p, which is the plasma frequency, and this plasma frequency is arising due to collective oscillations of the free electrons. To collective oscillations of free electrons, this plasma frequency is arising, and whereas this omega 0 is called Lorentz Sommerfeld frequency. Of free electrons. M star is the effective mass of the electron. And now at long wavelengths, that is in the far infrared region, this epsilon 1 value goes to 0, and epsilon 2 value it goes to infinity, and thus we have n is equal to k is equal to epsilon 2 by 2, and this is also equal to 2 pi sigma by omega. Now this relationship is expected to be valid in region of high damping. So this is valid in the case of region of high damping or high absorption. And in this case, omega is less than Lorentz Sommerfeld frequency, and omega tau 0 is also less than 1. So this condition is satisfied. Now typical metals, wavelength for the typical metals are in the region of 10 to 20 micrometers. In this range, this is actually the spectral range. The reflectance from a metal surface reduces to R is equal to 1 minus 2 omega divided by pi into sigma to the power 1 by 2, and this equation is known as Hagen-Rubin relation.